Hello and welcome back to chemistry practice. Today we are going to go over acids and bases. In the book there are three definitions of what makes something an acid. I'm going to focus on the first definition by a Swedish chemist named Arrhenius. In future videos I'll look at the other two. To be honest, if you know the Arrhenius definition well, you should be totally fine in introductory chemistry, except for a few minor exceptions. So Arrhenius was Swedish, and he's a famous chemist. Here's a picture of him right here. On the Wikipedia page, because that's where I go for all my information, it said that he was a boy genius and taught himself to read or learned how to read by 3. Okay. Needless to say, he's super intelligent. He won a Nobel Prize in chemistry. Apparently, there's a lunar crater named Arrhenius, and there's also a crater on Mars named after him, and there's a mountain named after him. So, if you have all those things named after you, you must be doing something right. This is beer. Specifically, Carlsberg, which is a Danish beer. Now, why am I showing you beer when this is supposed to be about acid and bases? Because Arrhenius actually worked in a laboratory funded by the Carlsberg Beer Company. As it turns out, when people are brewing beer, they want to know the acid content or how acidic the beer is. And before the 1900s, people just had certain ways of saying it's acidic, such as it's kind of acidic. It's a little bit more than kind of acidic. It's very acidic. As you can imagine, this led to all sorts of confusion, so Arrhenius was tasked with the idea of coming up with a scale, which he did. So, enough of the history. Let's talk about what Arrhenius actually came up with. Arrhenius defined an acid as something that breaks into hydrogen cations in a solution. So let me show you the most basic example. This is actually hydrogen chloride. Notice it's a gas, and that's how I would name it. But if I take hydrogen chloride and I put it in water, which is going to be my solvent, it will break into hydrogen ions, these are cations, and also chlorine anions. These are going to be floating around in the water. We've talked about this before. This is called dissociation, and this is an ionic compound. So that's sort of review. He discovered that any substance that donates hydrogen ions or breaks into hydrogen ions in something else is acidic, although they have varying amounts of power. So that's his definition. It's very simple. If I take some substance, I put it in a liquid, it's always going to be water, although there might be a few exceptions, and it donates hydrogen ions, then it will be an acid. He defined a base as something that donates hydroxide. So this is sodium hydroxide. If I take this and put it in water, it will break into sodium cations and hydroxide anions. The hydroxide makes it a base. So bases are anything that will be put into water and donate hydroxide anions. Yet again, some substances donate more than others, therefore some bases are stronger than others. Okay, let's go ahead and move on. That's fine and dandy. Now we know what makes an acid and a base, but what makes one acid stronger than another acid? And how do we actually get to this scale we've heard about called a pH scale? Well, to understand that, we first have to understand just the general concept of water. This is going to be slightly difficult, but stick with me. Water is a substance that is called amphoteric. What that means is that water can actually be an acid and a base. Okay, let's get a little bit more specific. Let's say we have 1 liter of water. Here's some water just having fun. 1 liter. Inside of this 1 liter of water, we have all of these water molecules. In fact, we have about 55.5 moles in 1 liter. As it turns out, every now and then, these water molecules interact in such a way where one water molecule will steal a hydrogen from another one, and then it will create a hydroxide anion, and this is called hydronium. So wait a minute, we just said an acid is something that donates or loses a hydrogen ion. So if water loses a hydrogen ion and donates it to the other water, it's actually an acid. But we also just said a base is something that donates hydroxide anions, which water can also do. And there's a nice little graph up here that actually shows it better, because here we see H2O, and there are 2 lone pairs of electrons on there. Now this one lone pair will grab a hydrogen proton. Why is this a proton? There's no neutron. It's plus, there's no electron. It's just a hydrogen proton, and it will bind here, making this H3O plus. There's a charge on it. And then the leftover water will be hydroxide. And actually, it will have some lone pairs after that, although don't worry about it. So you're probably thinking, whoa, mind blown. I've been drinking acid. Well, actually, no. First of all, in 1 liter, this happens so infrequently, it's very, very, very small. There's a very small amount of hydronium ions. There's a very small amount of hydroxide ions in 1 liter of water. Now, I want to clarify one thing really fast. If I have hydrochloric acid, remember this is in the water, and it donates this hydrogen. The hydrogen will never be floating around by itself in the water. The hydrogen will always combine with H2O to make hydronium. So oftentimes in textbooks or in class, you'll hear teachers refer to a hydrogen proton or a hydrogen ion or hydronium. They're really sort of referring to the same thing when we're talking about acid. Because remember, the hydrogen ion or proton must bind with a water to make hydronium. So this is actually what's floating around in the water, but it depends on the equation what people write. Sometimes in the equation, people will write it differently. So if this was hydrochloric acid, they'll just write it like this. But actually, keep in mind, it should be hydrochloric gas or hydrogen chloride gas plus H2O equals this and this, and there's a bunch of water too plus H2O, so there's water on both sides of this equation. There's just so much of it, people don't write it. So that is something that confuses people often. Okay, so back to what I was saying. In 1 liter of water, how many of these hydronium ions are there? Well, they've done experiments, and they have figured out that there are 1.0 times 10 to the -7. That's a tiny number. If I take this -7, remember I got to go this way 7 times, so it's point, and then I have 6 zeros and then 1 0. So it's tiny. It's not much. Now, if I have this many hydronium, I also have this many hydroxide. 1.0 times 10 to the -7 hydroxide per liter. Okay. Now, here's what is sort of confusing also. Let's look at the equilibrium expression. If we write this as an equilibrium expression, I'm going to write the products over the reactants. And in an equilibrium expression, I write the concentration, which is the molarity. So this is molarity. And I'll have this over 2 H2O. But remember, this is a liquid, and when we write equilibrium expressions, we don't include liquids because it's assumed that there's so much of it that it's in excess. So let's cross that out. And I'm going to write an equilibrium expression. Now, since this is water, K is the normal constant. I put a little W here. This is called the autoionization of water, or the equilibrium expression of water. There's different ways of saying it. KW equals, and now I have to multiply this, but really 1 times 1 is 1. But when I add these exponents, I'm going to get 1.0 times 10 to the minus 14. So that is a number we can use. Now here's what confuses people. Remember, we're referring to molarity, really, and this is just a ratio of moles per liter. It doesn't mean I necessarily have that many moles if I have less than a liter. So if I actually have 1 liter of water, then I would have 1.0 times 10 to the minus 7 moles of hydronium. Okay, I would also have 1.0 times 10 to the minus 7 moles of hydroxide. But if I have less than 1 liter, I'm not going to have as many moles. The molarity is going to be the same, though. That's what is really confusing. Think about it. Molarity, big M, or we refer to it as a concentration, is moles per liter. It's a ratio. So let's say I have a molarity of 10 moles per liter, right? Of whatever this is. If I have 1 liter, the molarity is 10, and I would have 10 moles. Okay? But if I have 100 milliliters, the molarity is still 10 moles per liter, but I'm going to have fewer moles in here and fewer representative particles if I look at Avogadro's number. So what I'm trying to say is, don't get confused between molarity, which is a ratio, and number of moles. You would have to do some stoichiometry to figure out how many moles or particles you have in something that's not 1 liter. Okay. So you're probably still wondering, wait a minute, why are you telling me about water? We were just talking about acids and bases. Okay, we know that water is amphoteric. We know that water can donate hydrogen ions or hydroxide ions. We also know it has very few of those in 1 liter of water. And we refer to water as neutral. So think about it. The amount of hydronium and hydroxide cancel each other out. So it's not acidic or basic. It's neutral. Now I can finally tell you about the pH scale. So Arrhenius decided to use this as this concept of making a pH scale to figure out how many hydronium ions are in any particular solution. He's like, you know what? A strong acid will by definition have more hydronium. A strong base will have more hydroxide. But here's the thing, if I think back to equilibrium, let's say I take some hydrochloric or hydrogen chloride, HCl, and I add it to this. I already have some of these floating around, I have some of these floating around. Now this is going to dissociate. I will have H plus or some more hydronium. We can do it that way. Well, let me do it this way. So wait a minute. I've added a lot more hydrogen ions here. So what's going to happen? Well, it doesn't really matter if this is 100 milliliters or 500 or a liter or 50 milliliters. What's going to happen is this hydrogen ion will bind with some water, and this concentration is going to go up. I'm going to have more. But if we think about Le Chatelier's principle, yes, we're bringing in some previous knowledge. If this concentration goes up, this is going to seek equilibrium. So what's going to happen is this expression is going to shift to the left. Really what is going to happen is the hydroxide will try to suck up some of this hydrogen. Well, think about it. OH plus H makes H2O. So it's going to try to make some more H2O molecules. Think of this as a big paper towel. It's trying to suck up some of these extra hydrogen ions, but it's not going to be able to suck up all of them. So really what's going to happen is the concentration of hydronium will go up, the concentration of hydroxide will go down. So remember, the concentration is a constant, 1.0 times 10 to the minus 7, and this is 1.0 times 10. So, well, I'm sorry, the constant is 1.0 times 10 to the minus 14. So what's going to happen is if this goes up, this must go down. And Arrhenius realized this. He said, wait a minute. In any solution, which is all water, there's going to be a lot of water molecules floating around, so I can use a self-ionization concept to use it to make a pH scale. Now you might be thinking, why don't we just say the pH is, and then we can say the concentration of hydronium ions. Well, as it turns out, that's a very unwieldy way of using numbers in a chemistry lab, and it's easier to just make a nice little basic scale. So what Arrhenius decided to do was make a logarithm. So he said pH of any solution, doesn't matter if it's just water. We could add hydrogen chloride to this. We could add anything else that donates ions, is going to equal minus the log of the concentration of hydronium ions. Now, why is he using a log? Because if you think about it, a logarithm is just really their exponents. He's condensing everything into a scale of 10, base 10, to try to make it a usable scale in the lab. So what do I mean by that? Brief review. If I have log 100 equals 2. If I don't put a number here, it's assumed it's 10. So what I'm really saying is log base 10 100 equals 2. So what am I saying? 10 raised to the second power equals 100. That's all I'm saying. 10 times 10 is 100. So log 1000 equals 3. Yet again, there's actually a little 10 here that we don't see. So 10 to the third power equals 1000. So when he started doing that, he came up with this pH scale. If I just calculate what the concentration of hydronium ions is in molarity and plug it into this equation, I can put it in my calculator and I will find its pH. It's that simple. Now if I want pOH, which people really don't use as often, but we're going to use it in class, I will take the concentration in molarity of hydroxide and plug it in over here. This is going to be OH with a little minus. This scale is going to go from 0 to 14. Now why is that? Because we already decided that really with this water dissociation constant, or water self-ionization constant, it's going to be on a scale of 0 to about 14, because as one goes up, the other one goes down, and so the best I'm going to do is get 0 to 14. Now, why did he put a negative here? Because it's just a pain to deal in negative numbers. If he didn't put a negative here, and I put in this hydronium concentration, it's going to be a negative number, and he didn't want to deal with negative numbers, so the negative numbers just cancel out. That's why that negative is there, for no other reason. Why do we have a pH scale from 0 to 14? Simply because it's based on the water ionization constant, and really, if you think about it, that's really the limit to how many hydronium ions you can put in the water and change this. Now, there's always going to be some very smart student who's going to say, wait a minute, what if I just pour a ton of hydrogen chloride into here, into this water? Surely I can get some pH lower than 0. And the answer is yes. Actually, this scale goes down below 0 and it goes above 14, but those are like super special lab conditions, and they're not really something you're going to see on a daily basis, so we just say it's from 0 to 14. Now, let's go look at pH. Here's the thing that's the key. If I calculate pH, which is minus the log of the hydronium concentration in molarity, the smaller the number I get, the more acidic it is. I know it seems sort of counterintuitive, but I'm looking for a low pH. A low pH means it's acidic. A high pH means it is basic. So this is going to be a very strong acid. Water, it has a pH of 7, remember? Now why is that? Because in water, the concentration of hydronium ions is 1.0 times 10 to the minus 7 molarity. So if I go above that, I have more hydroxide. If I go below that, I have more hydronium. And this kind of gives you a nice little scale of what that means. Hydrochloric acid is very strong. It dissociates 100%. So I'm going to have a lot of hydrogen ions in there. And over here we get milk, water's in here. Notice coffee. I drink a lot of that. Lemon juice seems pretty acidic actually. And notice you're thinking, wow, look how acidic lemon juice is. But does lemon juice kill you? No. Here's the crazy thing though. As I go up the scale, I'm actually going up by a factor of 10 every single time because it's a log scale. So if I have a pH of 1, it has 10 times more hydronium ions concentration than pH of 2. A pH of 1 has 100 times more hydronium concentration than a pH of 3. Okay, then this is 1,000 times more. So there's actually a lot more hydronium in these low pHs. So now you know why we have a pH scale. You know this equation. You know what amphoteric is. You know what water self-ionization is. And this just kind of shows you a little bit more about the concentrations. I wanted to show you hydrochloric acid, right? pH is 1.1. Sulfuric acid, H2SO4, 1.2. In the next video, we're going to get to this idea that some of these acids will not 100% dissociate. And some of them will donate more than one hydrogen. So this is a good example. Sulfuric acid, it has 2. It will donate the first hydrogen, then it's HSO4 minus. Then it will donate the second one. So it's donating 2. But the second one doesn't 100% dissociate. So depending on how much it dissociates will depend on how many hydronium ions you have, and it will then affect the pH. That's why some things are more acidic than other things. Okay, last thing. Always remember you need to look at these little phases. Okay, this is hydrochloric acid because it's aqueous. It's in water. If it's HCl, it's a gas, that's hydrogen chloride. It's not an acid yet. And remember, it's going to combine with water, which is a liquid, and it will produce hydronium and chloride, chloride anions. Notice this says it will dissociate 99.996%. That's what makes it strong. So almost all of this will break apart and dissociate. All of this will break apart. Okay? Now if I look up here, this is a much weaker acid. This is acetic acid. Notice that only 1.3% of this breaks apart. So actually, most of this is still floating around in the water. That's what makes one acid stronger than another acid. So in class, in the next lesson, we'll look at acids that dissociate 100% and acids that don't. Then we will also calculate pH, pOH, and hydronium concentrations. All right, well, I hope that helps you. If you have any questions, let me know.